Hi again. So iron isotopes have typically been applied to characterize the formation of low to moderate temperature hydrothermal mineralizing systems because it is at these lower temperatures where stable isotope fractionation will be greatest, and because iron is a redox sensitive element and will fractionate due to changes in redox conditions. Now, more recently, iron isotopes have also been applied to characterize the formation of higher temperature copper PGE rich systems. And although we do understand that iron isotopes do fractionate between sulfide liquid and silicate melt, our understanding of how they behave during critical mineralizing processes is still rather limited, really hindering our ability to apply them in any robust way to characterize these economically important systems. Now, given how other stable isotopes behave in these mineralized systems, it's well to presume that iron isotopes will also preserve a record of the mineralizing processes. But as we'll see throughout this talk here, the iron isotope composition of sulfides in the Eastern Gabbro are actually largely controlled by post-cumulus processes rather than the supersolidus processes that formed the mineralization. As I just mentioned, we're going to be focusing here on the Coldwell Complex in Ontario, Canada. The Coldwell Complex is located on the northeast shore of Lake Superior and was infused into the Mid-Continent Rift approximately 1.1 billion years ago. And all these samples that we're going to be looking at here are from the Eastern Gabbro, which is a composite pluton that wraps around the eastern and northern margins of the complex and comprises a variety of mafic and ultramafic rocks. And sampling focused on the variably copper PGE mineralized Marathon deposit, Fort Dams, Sally deposit, and Redstone. Most of the work done on the mineralization in Eastern Gabbro is focused on the Marathon deposit. So mineralization here and really elsewhere in the Eastern Gabbro is largely restricted to the Two Duck Lake Gabbro, which is a coarse to pegmatitic gabbro that exhibits a subophytic texture. Now, mineralization at Marathon occurs in three dipping lenses, which from bottom to top are the footwall zone, main zone, and W horizon. And each of these zones are characterized by distinct copper palladium ratios, with the footwall zone having the highest ratios and the W horizon having the lowest ratios. Now, looking at the sulfides, they're quite mineralogically variable throughout the Eastern Gabbro. So the footwall zone and main zone, they largely comprise variable amounts of pyrite and chalcopyrite, with the footwall zone being more pyrite rich. Now, there is pennantite in most of these zones, but the abundance is relatively small, and they occur as these small little blebs, as well as exsolution flames in pyrite. Now, the W horizon is quite unique in that it comprises a more copper assemblage of chalcopyrite and bornite, and there's very little pyrite. And I have to stress here, this is really the only zone in the Eastern Gabbro that contains any significant amount of bornite. And moving northwards, again, these deposits, they largely comprise chalcopyrite and pyrite, but there's also a significant amount of cubonite that we don't see at Marathon. Here we have a box plot looking at the variation in iron isotope composition of pyrite throughout the Eastern Gabbro. And we can see that it is consistently lighter than the isotopic composition of the mantle and exhibits an overall variability of around 1.3 per mil, which does not vary in any consistent way from zone to zone. Now, looking at chalcopyrite, we can see that it is generally heavier than the isotopic composition of pyrite and exhibits a greater variability of around 1.8 per mil. Now, unlike pyrite, the iron isotope composition of chalcopyrite does vary in a consistent way in the Marathon deposit, with the footwall zone being isotopically heaviest and the W horizon being isotopically lightest. Now, I have to point out here that some of the chalcopyrite in the W horizon are actually quite similar in iron isotope value to pyrite elsewhere, and this is going to be important close to the end of the presentation. So it has been well documented that three main processes controlled and modified the mineralization in the Eastern Gabbro, those being sulfide liquid removal, contamination by Archean sediments, and variations in R factor. And so the civil question that we want to talk about right now is, did these three main processes control the iron isotope values that we're seeing in the Eastern Gabbro? And if not, then what other processes could have done this? So starting off first with sulfide liquid removal. So we can rule this process out as having had an effect on the iron isotope values of the sulfides for two main reasons. Now, the first reason is that removal of small amounts of sulfide liquid is not expected to modify the iron isotope composition of a silicate melt away from mantle values. And we can demonstrate this using a simple Rayleigh fractional crystallization model. Now, looking at the model, we can see that in order to modify the iron isotope values of a silicate melt from mantle values, we have to remove anywhere from 10 to 50% sulfide liquid. Now, considering that nickel copper PGE systems typically experience in the range of less than 1% sulfide liquid removal, this really seems like an unreasonable way to explain the variability that we're seeing in the Eastern Gabbro. Now, the second reason is that the only zones in the Eastern Gabbro that are known to have experienced any significant amount of sulfide liquid removal are the northern deposits. And we know this because they have copper palladium values that are elevated relative to mantle values, but these do not correlate with iron isotope composition of their base metal sulfides. And moving on to contamination, again, we can rule this process out as having had an effect on the iron isotope values of the sulfides for one simple reason, and that is because the iron isotope composition of a sulfide liquid rapidly equilibrates to the iron isotope composition of the surrounding silicate melt. And we can demonstrate this again using an open system R factor model in which a contaminated sulfide liquid interacts with multiple pulses of mantle-derived silicate melt. Now, looking at the model, we can see that unlike sulfur and copper isotopes, which equilibrate to mantle values at relatively high R factors of around 10,000, the iron isotope composition of a sulfide liquid equilibrates at much lower values in the range of around 300. Now, this distinction is very important because it demonstrates that any variability in the iron isotope composition of a sulfide liquid caused by contamination would be rapidly destroyed early on in the evolution of that mineralizing system. So what about R factor? So if iron isotope composition of the base metal sulfides was largely controlled by variations in R factor, then they should correlate with both copper palladium and sulfur selenium ratios. Now, given the large discrepancy between the sulfide liquid silicate melt partition coefficients between copper and palladium and sulfur and selenium, and the relatively small fractionation factor for iron isotopes, then variations in R factor should generate a very large range in both copper palladium and sulfur selenium ratios, and a very small range in iron isotope values. And that's exactly what we see here with these model R factor curves. Now, the green, red, and blue curves simply represent the same R factor model, except specifically for the footwall zone, main zone, and W horizon, taking into account their pyrite to chalcopyrite ratio. Now, if we overlay the data here, we can see that the mineralized zones don't follow the model trends, and this becomes very apparent when we look at pyrite in the footwall zone and chalcopyrite in the main zone, where they exhibit a very large range in iron isotope values and a very small range in both copper palladium and sulfur selenium. So this is opposite to what we would expect to see. So clearly, these three key processes were not the primary mechanisms that controlled the iron isotope composition of the sulfides. So what other processes are there? Here we have a box whisker diagram looking at the variation in bulk rock copper sulfur ratio throughout the Eastern Gabbro. And we're looking at copper sulfur ratios because they serve as a proxy for the amount of pyrite, chalcopyrite, and bornite that we have in these zones, with a higher copper sulfur ratio indicative of a lower pyrite content. So looking at the marathon deposit, we can see that there's a consistent increase in the copper sulfur ratio going from the footwall zone to the main zone, to the W horizon, mimicking that decrease in pyrite content that we talked about earlier. And with this increase in copper sulfur ratio, we have a consistent decrease in the iron isotope composition of the chalcopyrite. So clearly the base metal sulfide, the base metal sulfide mineralogy is playing a key role in controlling the iron isotope values, at least of chalcopyrite. So we can quantify the effect that crystallization of variable amounts of MSS has on the iron isotope composition of chalcopyrite using a modified version of the isotopic mixing model from Lesher and Burnham. And when we do this, looking at the model, we can see that as more MSS crystallizes, the iron isotope composition of chalcopyrite becomes heavier. Now, when we overlay the data for the footwall zone, main zone, and W horizon, so including the iron isotope composition of the chalcopyrite, and the relative purite to chalcopyrite ratios, we can see that in general, the data follow the model trends. Now, the one problem with this model is that some of the chalcopyrite in the footwall zone and main zone, they are lighter than what is predicted by the model. Now, something that was not included in this model is the presence of pentlandite, which we know crystallizes from MSS alongside pyrite, and we know its abundance decreases generally from the footwall zone to the main zone. So given that pentlandite is isotopically heavier than pyrite, then the crystallization of MSS comprising both pyrite and pentlandite will increase the iron isotope composition of chalcopyrite to a lesser degree than if you simply crystallize MSS comprising pyrite. Essentially, the more pentlandite that you have in your mineralization, the greater the discrepancy between the measured and modeled iron isotope values of your chalcopyrite. So what does this all have to do with oxidation of sulfide liquids? Well, a typical sulfide assemblage comprises chalcopyrite, pyrite, and pentlandite, but some deposits have a more copper-rich assemblage comprising chalcopyrite and bornite and very little pyrite. So this copper-rich assemblage, which is present in the W horizon, has been suggested to be the result of oxidation of sulfide liquids, in which the FeS component is oxidized to FeO. Now, this oxidation process essentially serves to increase the copper-iron ratio of the sulfide liquid, allowing it to fractionate past the ISS stability field and into an assemblage comprising largely chalcopyrite and bornite. Now, the similarity in the iron isotope composition of chalcopyrite in the W horizon to pyrite elsewhere is consistent with this model because it demonstrates that the copper-iron ratio of the sulfide liquid in this zone was high enough to limit or prevent the crystallization of MSS, preventing iron 54 from being sequestered from chalcopyrite and essentially allowing chalcopyrite to obtain a lighter isotopic value. I know that was a lot of information in a very short amount of time, and so I want to break this down into 3 key points. And the first point is that the processes that are most critical to the formation of mineralization in these deposits are not the main factors that are controlling the iron isotope values of the sulfides. Rather, the evolution of the sulfide liquid and the amount and composition of MSS that crystallizes is the main control, at least on the iron isotope composition of chalcopyrite. And finally, in order to apply these systems in any, in order to apply iron isotopes in any robust way to assess these economically important systems really requires a strong understanding of the mineralogy of the sulfide mineralization. Otherwise, it'll be very challenging to interpret the variability that we will likely see. Thank you.